Okay, welcome back everyone after the Christmas break, and a Happy New Year to everyone. We resume our journey into the regularity of elliptic operators in divergence form, and the topic for today in chapter 11, lecture 11, is so-called off-diagonal behavior. I'll say in a minute what this means, and we will see also during the lecture where the name comes from. We are still looking at the main actors of our course, which are the divergence form operators. So we have a minus divergence, some coefficient matrix A gradient, and to make things easier and not to bother about boundary conditions, we will place ourselves in omega equal Rn, and this will be the setting for the rest of the course. So we will always stay on the whole space Rn. All these topics are interesting in particular, and also on domains and then with boundary conditions, but this is a topic for the project phase. And up to now we always looked at these operators on L2 of omega, so L2 of Rn, in a global way. And what will be different today, or what is the topic of today, is we will take subsets of Rn and look at the behavior of the operator on, or of the more specifically of the resolvent of the operator on subsets of Rn. So take two subsets, measurable subsets of Rn, and then the aim is, and think of these subsets as being far apart. So there is a set E somewhere, and somewhere else there's a set F. So everything we will do is of no interest if F intersects E or something like that. And the aim is, if you have a function u in Rn that is supported inside the set E, so we have a function whose support is only here. If you now apply the operator L and look at the function on F, you will evidently find 0, because L is a differential operator, so it's a local operator. So if you differentiate something that has support only here, you get 0 everywhere else. This is no longer true for the resolvent of the operator. The resolvent of the operator is a non-local operator, so if you start with something that is supported here and you do the resolvent, you will find probably a function that somehow lives everywhere. And the question is, what is the contribution of the resolvent of U measured on F? And is there some, and we will find there's some decay, so the more the F gets away from the E, the less contribution does the resolvent give on F. And there will be even an exponential decay in the distance of E and F. And that is what we want to quantify in this lecture. So the aim is, if you have a function U that is supported in E, what we then head for is estimates for the resolvent, or later on also 1 plus t squared times L to the minus 1, applied to U on F. As I said, think E and F far apart. Okay, that's the aim of today's lecture, and this is what is called off-diagonal behavior. And as usual, we have some general notation for this lecture. Part of it is already here. So A is again an elliptic coefficient matrix, complex valued. And there are ellipticity constants, and they are, as usual, denoted by small and capital lambda. So small and capital lambda are the ellipticity constants of A. So capital lambda is the L infinity bound of the coefficients, and small lambda is the ellipticity bound. And then we will always look at the distance of the sets E and F and this will be denoted by dist of E and F. So this is the Euclidean distance between E and F, and this will play a particularly important role in this lecture. Okay. And in order to get an idea what might happen, we go back to our model case. So we start with the Laplace operator. And the good thing about the Laplace operator, you can have an explicit formula for the resolvent on the whole space, and you can calculate things and look what is to be expected. So this is the first section of this chapter. It's about the so-called Bessel kernel and the negative Laplacian, and we will investigate this question for the Laplace operator on Rn. And the fundamental tool is that we can just calculate a formula, an explicit integral kernel for the resolvent of this Laplace operator, and this is Lemma 11.2. Consider the following function, capital G, defined on Rn, which is strictly positive valued, given by g of x is 1 over 4 pi, the right normalization constant, integral from 0 to infinity e to the minus pi modulus of x squared halves, e to the minus s over 4 pi, s to the minus n halves ds. So this is an indefinite integral that is absolutely convergent. So there is a singularity in 0 which is good enough to be integrable, and there is a singularity for s going to infinity, but you have this negative exponential here which makes it absolutely convergent. And the claim is that this function has an L infinity norm that is exactly 1. That's why we have the 1 over 4 pi in the beginning. And that this is the integral kernel for the resolvent of the Laplace operator. So if you apply 1 minus Laplace to the minus 1 to u, this is just convoluting u with this particular function g. So this is an explicit formula for how to calculate the resolvent. You just have to convolve with this function. And this function that's the reason why this is an important function, and this is the so-called Bessel kernel. I will not prove this in this lecture. We have a very tough program in this 11th lecture, but it's so the first claim is just do the integral and calculate stuff, and you get 1. And to prove this, one can use Fourier transform on both sides. Then you get here a multiplication instead of the convolution. You know how this is calculated because it's the Laplace operator. We know the symbol, and then it's 5 tonellis and some integration and looking at Fourier transforms, and you will find that this is the right formula. It's a very classical result, but the good thing is that now we know how the resolvent of the Laplace is calculated, and we can look at the off-diagonal behavior. So this question, how much contribution does it give the resolvent on the set F if the function u is only supported in E. Okay. And in order to look at this off-diagonal behavior, it's a good thing to get an estimate on this function g for large x. Why? Because the resolvent is given as the convolution of g with u. So what is of interest, so 1 minus Laplace to the minus 1 u of x is integral over Rn g of x minus y u of y dy. This is the convolution. Now we know that u is only supported in E, so this is a integral over E, because for y not in E this is 0. And so what? And if we have an x in F, so if we want to look at this in F, we have the difference of an element in F and an element in E here. So what is it of interest for answering this question, how much is the resolvent in F when we are only supported in E, is a question on what is G for arguments that have large absolute value. So we need an estimate for G for large estimate value, for arguments with a large absolute value. And this is what lemma 11.3 gives us. So this lemma says for large x we have exponential decay. So for every, there exists some constant such that you can estimate the value of g of x. I do not write absolute value here because g is positive anyway. So that g of x is bounded by a constant e to the minus modulus of x halves. And this is true for all x that are larger or equal 1. Okay. And the proof is estimating the Bessel kernel. So g of x written up there, okay, is less or equal up to a constant. Let's already put the 1 over 4 pi into the constant. The integral 0 to infinity. So what is up there? E to the minus pi absolute value of x halves, e to the minus s over 4 pi, s to the minus n over 2 ds. Okay. And what we do is we take these two exponential functions and split them into two halves. So x squared over, I did a mistake there, yes, it's minus x squared over s here, not over 2. So here's also an s. Yeah, otherwise it would be constant in s. It wouldn't be inside the integral. Okay, so we take a half of this one. So this gives us e to the minus p of p times x squared over 2s plus 1 over 8 pi, s over 8 pi. And then there is the second half part, e to the minus modulus of x squared over 2s, e to the minus s over 8 pi. In one I take the use the exponential, the functional equation for the exponential function. The other no, because that is how it's then estimated, s to the minus n over 2 ds. Okay, and now we do two things. In this exponential function here, I will use the inequality between geometric and arithmetic mean. So this is a arithmetic mean, x squared over, of the two numbers x squared over s and s over 4 pi. And we can estimate this so by the inequality between arithmetic and geometric mean. The arithmetic mean is always larger than the geometric one. We get that pi x squared over 2 over s halves plus s over 4 pi halves. This is this exponent. This is larger or equal than the geometric mean, which is the square root of the product of the two. So this is square root of pi x squared over s times s over 4 pi. And this is already fine because many things cancel out. So the s cancels out, the pi cancels out. You had to have a square root of x squared over 4. So this is exactly modulus of x halves. So we made this smaller, so there's a minus sign here, so we make everything bigger by putting this estimate in. So this is less or equal 0 to infinity e to the minus modulus of x squared, and in the second part you just use that modulus of x is greater or equal 1. And since modulus of x is greater or equal 1, this here is you can estimate the x squared by 1. This gives this makes this one smaller, so the whole thing bigger. So what you have is e to the minus pi over 2s, e to the minus s over 8 pi, s to the minus n halves ds. So we use this inequality, and just in the second factor, just that the modulus of x is greater than 1. Okay, so this does not depend on s. You can take it out of the integral. And the rest just only depends on s and is an absolutely convergent integral, which gives you just some number. So what you have here is the value of the integral that I do not want to calculate times e to the minus modulus of x halves. And this is exactly what we wanted to show. Okay, so this is the behavior of the Bessel kernel for large arguments. And as I showed here, this is what we need to answer this question: what happens if E and F are far apart? Okay, so this leads us to so-called L2 off-diagonals for the negative Laplacian. So this is proposition 11.4. L2 off-diagonal estimates for the negative Laplacian. Okay, and the claim is there are constants, capital and small c, strictly positive, such that for every choice of measurable subsets in Rn, and for every u in L2 of Rn that has support inside E, so the situation I described earlier, it holds that if you take u and put it into the resolvent of the negative Laplace operator, and then measure this in L2 norm on F, that's what we want to do. We want to estimate the resolvent of the operator on F, and we want to see how this depends on the norm of u on E. And the claim is that this is less or equal than, the constant capital C, then the exponential decay e to the minus small c distance of E and F times the L2 norm of u on E. So this tells you, if you start with a function u and you look what the resolvent does on F, and if the F goes farther and farther away from E, then the contribution decays exponentially in the distance. And you also see here, this is of no new information if, for instance, E and F are the same set or something like that. Because then this is just the usual estimate, that you get by M-accretivity of the operator, that the resolvent is bounded by some constant. So the interesting case is when E and F is far apart. Okay. So let's prove this. So take two measurable subsets of Rn and take some L2 function on Rn that is supported in E. And then we distinguish two cases. So the first case is easy. The first case is if E and F are close together. But as I was already said, this is the non-interesting case. So if the two are close together, then in fact we already know the estimate, because what you then simply do is, okay, you want to estimate the resolvent of U on F. You just estimate by the resolvent of U on the whole space. So this is less or equal than the resolvent of U in L2 of Rn. Then we know that minus Laplace is an M-accretive operator, so the resolvent is bounded by 1 over lambda. Okay, lambda is 1, so this is bounded by 1. So this is less or equal than the norm of U in L2 Rn. Okay, now U is only supported in E, so you can put an E here. And this is the off-diagonal estimate that we search for. You might ask, where is the exponential decay? Okay, the distance is less than 1. So this is less than E times the distance of E and F times the norm of U in L2 of E. And because I know the distance is less than 1, E times E to the distance is less than 1. No, there's something. E to the minus distance. So this is the off-diagonal estimate with constant E and constant 1 here. Okay. So the interesting case is what happens if E and F are far apart. So far apart in this case means distance less than greater 1. The 1 is completely arbitrary. You see, this argument can be done if the distance less than 5, then I take E to the 5 here. But I need some cut. 1 is the easiest choice. Okay. So now we really have to go into the weeds and do calculations. Now we need the Bessel kernel. Up to now it was just abstract things. But now we need the special structure of the resolvent of the Laplace operator, and in particular our estimate from the preceding lemma. So what we want to estimate is the L2 norm of the resolvent on F. So let's look at the modulus of this function squared. So let's look at this one. Then we know how to calculate the resolvent. The resolvent is just convoluting with the Bessel kernel. So this is the Bessel kernel at x minus y, u of y dy, modulus squared, and we should integrate over Rn, but as already pointed out, u is only supported in E, so we can do an integral over E here. Okay, now we want to apply our exponential decay, and if you now use the exponential decay, okay, you can put in the absolute value inside the integral. We'll do this in a minute. But if you then use the exponential decay on all of g, you will lose the convergence of the integral. So this is too brute force. What we have to do is somehow we have to reserve. We have to take one half of the g for the estimate and one half of the g for the integral. So split the g into g of x minus 1 y square root times g of x minus y square root u of y dy. This is possible because g is positive. The Bessel kernel has values in the strictly positive real number, so we can take square roots. And in the same time, I put this absolute value into the integral for less or equal. Okay, now we do a Cauchy-Schwarz inequality. So, well, with these two factors, so this is the first factor and this product is the second factor. And this gives me, so if you look at the first factor, you do a square an integration, you just get the L1 norm of G squared. So this gives you the L1 norm of G squared. We already know this is 1. So this is a nice part. This is 1. And then, no, it's even not squared. It's to the 1/2 and then squared. So this is okay. And then the second part is integral over e, the square of this one to the 1/2 to the square again squared. So it's only square of this one. So it's g of x minus y, u of y in modulus squared dy. Okay. So all this Cauchy-Schwarz was somehow to get the square inside the norm. Now we have u squared. This looks already nice because in the end we want to have L2 norm of e on e. Okay. So plugging this into the norm that we want to estimate. So we want to estimate 1 minus Laplace to the minus 1 u in the L2 norm on f. And to make a simpler writing, let's estimate the square of this one. Okay, this is the integral over f of the term that we just looked at, 1 minus Laplace to the minus 1 u of x modulus squared dx. So this is what we just estimated. So let's put in the estimate here. So this is less or equal integral over f. This was 1 integral over e g of x minus y u of y modulus squared dy dx. Okay. Next thing evidently is to do some Tonelli. So this is integral over e. I just want to have integral over f g of x minus y dx modulus of u of y squared. Okay, and now we can use our decay property of g, because now we know that x is in f, y is in e. So we know that that this number here has a modulus of at least 1, because e and f are more than 1, at least 1 apart. So this is exactly Taylor-suited to our lemma before. And in order to use it in the right way, the best thing is to now switch to polar coordinates in this thing. So we still integrate over e, but we replace the integral over f into polar coordinates, which is a good thing because this function g is radially symmetric. So the Bessel kernel is a radially symmetric function. If you look at the dependence on x, this is in modulus. So polar coordinates are the right thing. And if you have a radially symmetric function and you do polar coordinates, all the integrations in the angles give you the surface measure of the unit surface. So this is sigma n minus 1. And then there's the integral over the radius. And so we have to integrate, but we do not have to integrate over all radius, but only over functions where r times the direction of x lies in f. And then there is g on the sphere with radius r, so I just take the point r times e1. E1 is the first unit base vector, just to have one point on the sphere with radius r. The function is radially symmetric, so it doesn't matter which one I take. And then there is the determinant of the substitution to polar coordinates Rn minus 1 dr. Okay. Now we know that this indicator function surely is 0 for r less than the distance of e to f. So if r is less than the distance from e to f, this thing will never be in f. So this is less or equal integral over e. And let's also put this sigma n minus 1 into the constant. And we can here integrate from the distance of e to f up to infinity, and then let's integrate everything that is left. Okay, now we integrate also on huge parts that lie outside of f, but I do not care. This will give me the right estimate. Okay, and now here we can put in our off-diagonal estimate, our estimate on G for large values, and this gives, so this is 11.3. This gives us integral over E, integral from the distance of E to F to infinity, and then the G can be estimated by e to the minus r over 2. This is exactly lemma 11.3. dr u of y squared dy. Probably this is missing here. Yeah, this is missing here. This is missing here. And this is missing here. Okay. Okay, and now this thing in the middle we can just integrate. Yeah, but before we integrate, let's even make it easier. So this is some polynomial times an exponential decay, and we can estimate this from above by a little bit less exponential decay without the polynomial. So up to a constant, we can estimate this by integral over E, integral for the radius going from the distance of E and F to infinity, e to the minus r over 4. So I give away a little bit of the exponential decay, and for this get rid of the polynomial. Okay, and now if you calculate this exponential integral, it will give you up to a constant exactly what we want to have. So this is less or equal e to the minus distance of e to f over 4, integral over e, absolute value of u squared dy. So this is nice because this gives us the L2 norm of u on e, and this is the exponential decay, so this gives us the off-diagonal estimates. Okay. So why is it called off-diagonal estimates? Because we look at G for huge arguments. So this relies on the estimates of the function that to x and y assigns g of x minus y. So this was the function, this was the main estimate in all this calculation, was that this function here has an exponential decay, and for x far apart from y, and this means if you look at it like this, so this is a function in two variables, and what we need is an estimate for x far apart from y, so far away from the diagonal. And this is why it is called off-diagonal estimates. So these are estimates for the kernel. You need for the off-diagonal estimates for the operator. If the operator is given by a kernel, translate to estimates of the kernel away from the diagonal. That's why it's called off-diagonal estimates. So this is off-diagonal. Okay. Okay, now we've seen what happens for the Laplace operator. So there indeed is an estimate to know how large the resolvent can be on some set f if you know that your function is supported in E. You even have a nice decay, an exponential decay. And the obvious question now is, can we have the same thing for more general operators, in particular for our class of elliptic divergence form operators? And this remains to be checked, so the natural reflex is to put this into a definition. So this is definition 11.5. And what I've shown to you now is that the one operator, 1 minus Laplace to the minus 1, has these off-diagonal bounds. Natural question also is, what is about the whole resolvent? So if it's not 1 minus Laplace but lambda minus Laplace, and how does the estimate depend on lambda? In fact, this is more or less a scaling question. So there is an exercise you're invited to see this. If you have one point on the real line like the minus 1 here, where you have an off-diagonal estimate, then you can get the scaling in lambda just by scaling your estimate. You do not need to redo the proof for lambda. You can just do the right substitution and everything works out. And that's why I will formulate this off-diagonal estimate definition for families of operators. For resolvents, in fact, the first occurrence of this notion in the literature even wasn't for resolvents, but for semigroups. So this was a semigroup thing, the off-diagonal estimates. So it's natural to formulate it for families of operators. Okay, so the family t greater 0. But if you're confused by this family, just think of t equal 1 for the moment. Yeah, just take one operator. That's not the point. So a family of operators, of bounded linear operators on L2, is said to satisfy L2 off-diagonal estimates if you have the same behavior as for the Laplace here. So if there are constants capital and small c strictly positive, such that for all choice of measurable subsets E and F of Rn, and for all u that are supported in E, you get the estimate that the operator tt applied to u, measured in L2 on F, is controlled by, some constant, then exponential decay e to the minus constant small c, distance from E to F, and now the scaling in t is here. The right scaling is divided by t. Times the L2 norm of u on E. So this is now a definition. And somehow it tells you an operator has off-diagonal bounds if it behaves like the Laplace resolvent here. So if you have the same or similar by constants exponential decay. In the following, we will not only have this for scalar value for operators that apply to scalar valued functions, but also to operators applied to vector valued functions or vector valued operators. So in particular gradients, and there it's the same. So same definition for tuples of L2 of Rn functions applied component wise. We will in particular look at gradients of these functions in the following, so then you have tuples. As I said, this notion first appeared in the context of semigroups. It was a contribution of Gaffney in the 50s, and they were then reused and made popular by Davis in his groundbreaking work on semigroups, and that's why they also often called Davis-Gaffney estimates. So this is, if you find this in the literature, this is more or less synonymous to off-diagonal estimates. Okay. So what we are aiming now for is to prove that our elliptic divergence form operators themselves have off-diagonal bounds. And we will see. So the first try would be, okay, let's take the proof for the Laplace operator and adapt it. And this is a idea that does not work, because this was based on explicit knowledge of the kernel and calculations on the kernel. And for a general elliptic differential operator, you will not have a kernel. You cannot calculate it, and even worse, we will see later, there are elliptic differential operators in divergence form whose resolvent behave rather differently and who cannot have a kernel that has somehow the same behavior as for the Laplace operator. So this approach is blocked from the beginning. We have to find something completely different. But nevertheless, the idea is to prove the same things, and that's the second subchapter. So somehow this first chapter was to get the ideas and to see what we can expect. It cannot be better than for the Laplacian. But we will see it's of the same quality as for the Laplacian. So off-diagonal estimates for elliptic divergence form operators. And the first thing we will do is to look at the case E equal F equal Rn. So if there are off-diagonal estimates, then they are for all choices of E and F. So in particular, you have to have them for E equal F equal Rn. In this case, this translates to uniform estimates in T. If E and F both are Rn, this distance is 0 here. So the exponential factor is not there. And what you get is that TTU in the norm in L2 is bounded by some universal constant that does not depend on E and F and nothing, times the norm of U in L2 over N. So this means a necessary condition for off-diagonal estimates to hold is you have to have uniform estimates in T. And that's the first thing that we want to prove. That is Lemma 11.7. So for all U in L2 Rn, so E is now Rn, and for all T positive, the norm of 1 plus T squared L to the minus 1 U on L2 over N is bounded by, it's even less or equal the norm of U in L2 Rn. So this is off-diagonal estimates for E equal F equal Rn. It's for the moment perhaps a little bit peculiar choice to call the resolvent parameter T squared and not T. and to write it at this point. But for all these considerations, this is the good thing to do. And we've seen this way of writing the resolvent already several times. So we do a squared scaling here, 1 plus t squared L. But if t is a positive number, this gives you all the resolvents on the positive real axis, negative real axis. Okay. This is nothing new. This we already proved in Theorem 221, because we know that our operators L are M-accretive, and M-accretive gives you this estimate. Okay, so this is just Theorem 221. But I told you we also want to look at gradients. We want to show that these operators have off-diagonal estimates, but we do not only want to have this family, but also the family t times gradient times 1 plus t squared L to the minus 1u. Okay, and this and this is now L2 to the Rn to the n, because the gradient has n components. And I claim that also for this you have uniform estimates in t. So this is, I claim this is bounded by square root of 2 over lambda. Lambda is the ellipticity constant of our coefficients. I remind you. So this is notation 11.1. So this is the ellipticity constant of the coefficients times the L2 norm of u. Okay. So to prove this, as I already told you, A is done. So this is old stuff. Let's go to look at B. Okay, so what we are interested in is the gradient of this function here. Let's call this W. So W is 1 plus t squared L to the minus 1u. And then what we want to estimate is the norm of t gradient W in L2 of Rn to the n. This is what we want to estimate here. And let me take the square of it and multiply with lambda. So then you can get out the t squared. So this gives you t squared times lambda times the gradient of W measured in L2 Rn squared. Now you can use ellipticity of the coefficients. Ellipticity of the coefficients tells you exactly that the real part of the quadratic form is bounded from below by lambda times the square of the gradient of the function. So this is ellipticity of the form. Real part of the form is bounded from below by ellipticity constant times the square of the gradient. So this is ellipticity of the form. Now we can use the definition of L. Why? Because the W is in the domain of L. And the W is a resolvent applied to U. So it's in the domain of L. So this is t squared times the real part of the scalar product of LW applied to W. And this is a L2 scalar product here. Now estimate the real part by the modulus and take Cauchy-Schwarz inequality. Gives you t squared times LW in the L2 norm of Rn times W in the L2 norm of Rn. And now the important trick or the important point is to see that LW or that t squared LW is the same as U minus V W. Why? If you apply t squared L to W, so t squared LW is t squared L plus 1 t squared L plus 1 to the minus 1 u minus u, minus w. T squared L plus, no, minus, so this is a u here. Okay. T squared L times this is that, and then you have 1 u left minus u. So, and this is minus w, and this is u minus w. Okay. So this is u minus w in the Rn norm times w L2 Rn, and the rest is now brute force estimate the difference of u minus w in L2 by the sum of the two norms. So this is less or equal the norm of u plus the norm of w times the norm of w. We know from A that you can estimate the norm of w by the norm of u. So this is less than 2 times norm of u times norm of u. And yeah, so this is norm of u squared. You take the square root, you divide by square root of lambda, and you're done. So this is the 2 up here, the lambda from here, and taking square roots. Okay, so now we did all the preparations to do the great result of today's lecture. So the rest of today's lecture will now be to prove the L2 off-diagonal estimates for our elliptic operators, starting from this, somehow first necessary thing. I hope I convinced you. If you do not have these, there cannot be off-diagonal bounds. There's a long way to go from here, because this is only Rn. This is the special case equal F equal Rn. So there's a way to go, but this will work out, and we will look at this after the break. Okay, let's start again and formulate the off-diagonal estimates for our operators as already announced. So this theorem 11.8 is about L2 off-diagonal estimates for L. And what we will prove is that the family is 1 plus t squared L to the minus 1. So the resolvents of L for t greater 0 and t times the gradients of the resolvents. So the gradients of the resolvents also fulfill off-diagonal estimates if you do the correct scaling, so if you multiply by t. So t times the gradient of the resolvents is also a family that satisfies L2 off-diagonal estimates. And in these off-diagonal estimates, there were 2 constants, capital C and small c. And what we can also do is, during the proof, track the dependency of these constants. We will not write them out, but we will see on which data they depend. And the good news, and which is worth writing it down, is that these constants, obviously, they depend on the operator L, and in particular on the coefficient matrix A. But they do not depend somehow on the coefficient matrix, but the only characteristic numbers of the coefficient matrix that go into the play are the ellipticity constants capital lambda and small lambda. So if you have coefficient matrices that have a common ellipticity constants, you will get uniform off-diagonal estimates for this class of coefficient functions. This is worth noting. Okay, so let's do the proof. So what do we need? Okay, we need two subsets of Rn, measurable subsets. We need an L2 function U that is supported inside E. So support of U is contained in E, and we want to estimate the resolvent at T times gradients of resolvent of U on F. As in the lemma before, we will call the function 1 plus t squared L to the minus 1 applied to U. We'll call this F. We will call this W. And I will also abbreviate the distance of E and F because I have to write it down often, so I will just write D for this distance. So if we now think back on the proof of the L2 off-diagonal estimates for the Laplace operator, there were two cases, because L2 off-diagonal estimates are not interesting if E and F are close together. So that was the easy part, if E and F are close together, and if the interesting part was if they are far apart from each other. So we'll mimic this and do the same case distinction more or less. So we will first look at the distance being small, but we will see later in the proof that it's a very good idea to now not just to say we do a case distinction D smaller 1 and greater 1 or greater equal 1, but we will introduce one more parameter in this case distinction. So to at the moment still be free where to cut the two cases, and we will see that this parameter will be very precious during the proof, because at one point we can choose it in the right way to make several things disappear. So the case 1 is not distance less or equal to 1, but the distance less or equal than some parameter alpha still to be chosen times t. So we cut the two cases in function of t by this coefficient or this parameter alpha to be chosen later. Okay, but this is again the case where the distance is small somehow. And in this case, again, the estimate somehow is more or less our lemma 11.7. So our uniform estimate on the whole space. So we do the same as for the Laplace operator. We do a really crude estimate. So what do we have to estimate? We have to estimate W in L2 of F. So this is our family applied to U. And we want to estimate T times the gradient of W in L2 of F. I will do it both at the same time. So this is the two families that we want to. So there's a T inside the W. So this is the two families that we want to estimate against the norm of U on L2 of E. Okay, and we do the same as before for the Laplace operator. We estimate this by the norm of W and T gradient W on the whole of Rn. And then we apply lemma 11.7. So our uniform estimates on the whole space. And this gives us, so this is 11.7. This gives us, okay, this is estimated just by U. Norm of W and Rn is estimated by U, and the other one is estimated by square root of 2 over lambda times U. So this is less or equal 1 plus square root of 2 over lambda times the L2 norm of U on Rn. Again, U is only supported in E, so you can write down, you can replace this by E. And then you can again smuggle in the exponential decay. So this is less or equal e to the alpha, e to the minus d over t times the L2 norm of U on E. Because alpha d over t is less than alpha. So this is less than 1. And this gives you the off-diagonal estimate. So this off-diagonality e to the minus distance over t. This is exactly what you have to have for off-diagonal estimates. E to minus distance over the scaling t. This is here for free because the distance is bounded. Okay. Off-diagonal estimates are only interesting for large distances. That's why the proof is so easy for small distances. Okay. Okay, case 2. We look at the interesting case. The distance is larger than alpha times t. And yeah, this proof is really something amazing because I can present it and I hope you will say, yeah, this works. But as often for the really beautiful proofs in mathematics, the right question is, how on earth did someone find this idea? So the idea is simply stated, you just take the right equation and test with the right function. Okay, the equation is the resolvent equation, that's okay, but the right test function that you use, this is just genius. So what is this test function? And this is one of the many ideas that somehow came or were produced during the long hunt after the Kato square root property. So you find this idea also in the main contributions to the Kato square root property. It's surely based somehow on ideas of Davis, but it's one of these ideas that came along during this journey. And so what is the test function? We start with some cutoff function. So take a bounded C infinity function on our Rn that is 1 on F and 0 on E. So classical cutoff thing. E and F are far apart. So you can find such a nice differentiable function that is 1 on F and 0 on E, and you can even control the gradient because you know the distance. So the distance times the gradient of rho in the L infinity norm, this can be bounded. So the gradient is bounded by some constant over the distance of the set. Okay. And then it's also important to note that this constant here depends only on space dimension. I told you we want to take track of dependence of constants. This is just a question of geometry of Rn. So this depends only on space dimension. Okay, and now the idea of the proof is take the equation 1 plus t squared L applied to W is U. W was the resolvent of U, so if you apply 1 plus t squared L to W, you get U. So take this equation and test it. So do a scalar product of this function with the following function called V, which is W times E to the D over alpha t times rho minus 1. And this is something you have to write down. So you take this test function. We have to make sure that this is a nice function that we can work with, but we will see. And multiply this equation, and then we will do the right magic and it will work out. So this part of the function, here's a squared missing. This part of the function without the squared, I will call eta. So eta is this exponential minus 1. So let's collect properties of these functions eta and v, which will help later. So the first thing, this function eta is also a C infinity function. It's an exponential. There's the rho inside. There is this d over alpha t. Note d over alpha t is strictly greater than 1. Because we are in the case d is greater than alpha times t. So this is some number strictly greater 1 times rho minus 1. This is C infinity. I claim it's not only C infinity, it's even H1. So it's weakly differentiable for sure, it's C infinity, but what this means, it has an L2, it's in L2 and the gradient is in L2. Why? Because it's a bounded function and it's bounded with bounded derivative on a compact, with a compact support. Bounded derivative, and it has compact support. Why has it compact support? Because function eta. Whenever the rho is 0, this function is 0. No, nonsense. So the eta it's not the eta in H1, it's the V in H1. V is in H1, and then it makes sense. Because eta is bounded with bounded derivative, and W is in H1. W is in the domain of the operator. W is in the domain of the operator, so it's in H1. This is bounded with bounded derivative, so the product is in H1. That was the important point. Okay. Then next thing, as I already told you, eta is 0 on E. On F. Eta is 0 on E. Why? Because on E the rho is 0, so this is 1. You have 1 minus 1. And on F, it's evidently non-zero, but we can estimate how large the contribution on F is. So eta is given by e to the d over alpha t minus 1. We can estimate this from below by e to the d over alpha t minus 1/2 e. This is just using that e is greater than 2. And then we use that this exponent is greater than 1. So I can put it here. So e to the d alpha t. I even subtract more if I put the same exponent here, because this exponent is greater than 1. So this is subtracting more, so making things more negative. Okay, but this is just 1/2 e to the d over alpha t. This is an estimate that holds on F, because on F the rho is 1. So on F the rho is 1, so the eta is just e to the d over alpha t minus 1. And on F we know it's greater than 1/2 of this exponential. Yes? Because this is our case. D over alpha t is less greater than 1. So this is using that e and f are far apart. And the last thing, we want to estimate the norm of the gradient of eta. And this is, okay, what is the gradient of eta? We have to calculate. So this is this exponential will reappear, and then we have this factor times the gradient of rho. So this is d over alpha t gradient rho times e to the d over alpha t rho. And now the gradient of rho is bounded by c over d. So this is less or equal c over d. So this is less than c over alpha t. So the d cancels. times, and this is more or less eta. What is it? This is eta plus 1. Okay. And we have the modulus missing. Okay. Okay. So now let's do what was the idea. Take this equation and test with v. So v, we can multiply this equation, scalar product on left and right, with v. So what we get is scalar product of u and v in L2. And this is the easy part. This is 0. Why? Because u is supported in E, and the eta is 0 on E. Eta is 0 on E, so the v is 0 on E. U is supported in E, v is 0 on E, so the scalar product is 0. Okay, let's see what we get on the other side. So this is the scalar product of 1 plus t squared L applied to W. So this is U with V. Then this is the scalar product of W with V plus t squared L W V. T squared scalar product of L with W V, but this is just the, by the definition of L, this is the form A of W and V. This is definition of our operator given by the form. Okay, so we can go to the coefficients. Write this scalar product as an integral. What do you get? You get W times V. W times V gives you W times W bar, okay, so this is double modulus of W squared, times eta squared. Bar, but eta is real, so the bar is of no importance. Okay, so this is the first integral, and here we have t squared integral over Rn coefficient matrix A applied to gradient W times the gradient of V, and V is W eta squared. And this is complex conjugated. Okay. So, calculate this gradient. So this is integral over Rn W squared modulus W squared eta squared plus t squared integral over Rn A gradient W. Okay, this is a product rule. This gives you eta squared times the gradient of W plus 2 eta W gradient of eta. And we have to see where we have to put the bars. So eta is real, so this needs a bar. Eta is real, this needs a bar, this is real. Okay. So what we will do next is take this term here to the other side. So there's 0 on the left, so take this term on the other side. This gives you integral over Rn W squared eta squared plus t squared integral over Rn A gradient W bar eta squared equals minus t squared integral over Rn A eta gradient W 2 W bar gradient eta. So this is just putting the one term to the other side. And this is now the equality that we will estimate. And so we will make an estimate out of this by estimating this from below and this from above. So this left-hand side here, so now this is a complex number, so you cannot estimate it, but you can estimate the real part of it. So the real part of this we can estimate from below by, okay, we just keep the first integral, Rn w modulus squared eta squared. And here we use the ellipticity of our coefficients. So this is a times some vector bar. So this is exactly made for ellipticity. We take the real part, and then this is greater or equal than lambda times t squared times integral over Rn gradient of w squared eta squared. Okay, this was ellipticity. And on the other side, we bound the absolute value. Note this is okay, so in the end you have real part of this thing, so this is less than real part of that. Real part of that is less than modulus of that. Modulus of that is this one, and now we can estimate this from above. So what do we get? We get this is less than, okay, we have the 2 here, we have the t squared. And here we use the other ellipticity thing, we use the upper ellipticity bound, so the L infinity bound on the coefficient, so we get the constant capital lambda, times the integral of Rn modulus of eta gradient w times the modulus of w gradient eta. Okay. Why is this nice? So now you have to read it as an inequality. This thing here, less than the real part, less than the absolute value, less than the absolute value of this, less than this one. So we have this one, less than this one. Let's write this down. Okay, so this is integral over Rn modulus of w squared eta squared plus lambda t squared integral over Rn gradient of w squared eta squared is less than t squared. I will put the rest of the constants inside the thing. Rn eta gradient w times 2 capital lambda w gradient eta. Okay, why do I do it in this particular way? Because what I will now use is so this is a product of 2 terms, and I will estimate by what is sometimes called the Peter-Paul inequality. So this is less or equal epsilon over 2 times a squared plus 1 over 2 epsilon times b squared. So if you take epsilon equal 1, this is the usual Young thing, but you can sneak in this little epsilon, and it's called Peter-Paul inequality in reference to you have to rob Peter to pay Paul. Yeah? So you have to take something from one of the factors and put the rest to the other. Yeah? And we will use this inequality with the right epsilon for this factor here. And the right epsilon will be lambda. And you will see in a minute why lambda is a beautiful epsilon. So if you do this here with epsilon equal lambda, this is bounded by lambda over 2 times eta gradient of w squared eta squared plus 1 over 2 lambda. Okay, we have the 2 capital lambda squared. So 4 capital lambda squared modulus of gradient eta squared modulus of w squared. So this is this inequality applied here with the epsilon equal lambda. Okay, why is this beautiful? Because now you get an integral t squared lambda over 2 gradient w squared eta squared, and here you have an integral lambda t squared gradient w squared eta squared. So this integral here is exactly half of this integral, so you can absorb this term to the left hand side. And somehow this is the main program for the rest of this proof. Note this function eta might be awfully large. We've shown some estimate for eta. It's bounded from below by some exponential factor. That's not particularly nice. Yeah? So this eta might be large. The only thing we know on E is 0, yeah? But outside it might be large. So every eta on the right hand side is bad. So the main point is all these calculations that I do now and that we'll follow only are there in order to get all the etas to the left hand side. And this is the first step in this challenge, to get all the etas to the left hand side. So this is lambda t squared over 2, and this is exact. I can absorb this to the other side. So this gives me integral over Rn w squared eta squared plus, now take this to the other side, lambda t squared halves integral over Rn gradient w squared eta squared is less or equal, and we are only left with this one, t squared integral over Rn let's take all the constants out now. So this is 4 over 2 is 2 capital lambda divided t squared divided by small lambda. This is capital lambda squared. Times the integral over Rn, and we are only left with this one. So we are left with this one, yeah. Gradient eta squared w squared. Okay, this is our new estimate, and as I told you, the point is every eta on the right hand side must vanish. So this eta still has to go to the left hand side. And this is now where our estimate that we did before for the gradient of eta comes in handy. So if you look again at the upper blackboard, could you please? If you look again on the upper blackboard, there is the estimate of gradient eta of the modulus, which can be estimated by the modulus of eta. And this is now the match winner in this point. So gradient of eta can be estimated by a constant over alpha t times eta plus 1. So we can estimate this gradient here. So we know that gradient of eta squared can be estimated by c squared over alpha squared t squared of eta plus 1 squared. So there's a modulus here, but squared does the same trick. And now use some easy binomial estimate to even estimate this by 2 c squared alpha squared t squared times alpha squared plus 1. And then put it in here. This gives you that. So this, we can continue this estimate here by 2 capital lambda squared t squared over small lambda times integral Rn, and now put in this estimate. So this gives more constants. This gives 2c squared divided by alpha squared t squared integral over Rn modulus of w squared times eta plus 1. And now eta squared plus 1. which is also important. Now we see that again we might have a chance to absorb this term to the left hand side, because here we have an integral modulo of eta squared of w squared eta squared, and here we have an integral modulus of w squared eta squared. So we can absorb this term with eta to the other side if we somehow can get this awful constant here less than 1. We somehow have to see that this constant is less than 1, then this term goes to the left hand side and we have a perfectly nice estimate. Okay, and this is the point why we all the time bothered with this alpha. Now the alpha helps. We can choose alpha. Alpha is just a positive number. Up to now we have no restriction to alpha. It must be positive, strictly positive, but nothing else. And now just choose the right alpha to make this awful coefficient 1/2. And this is now just calculating what you have to do. So the right thing is take your alpha to be 8 over lambda square root times lambda times c. If you do this, so the t squared already cancels here. And if you do this, you will find that this is exactly, that gives you 1/2. So in this case, this is just 1/2 times the integral Rn w squared eta squared plus 1. And now we can absorb the awful term to the other side, and we end up with 1/2 integral Rn modulus of w squared eta squared plus lambda t squared over 2 integral of Rn modulus of gradient w squared eta squared is less than, and what is left on the right hand side is just integral over 1/2 of w squared. And now all the etas are on the left hand side. And if we now put everything together, we find our off-diagonal estimates. Okay, so this was a long estimate and calculation. What is the aim? The aim, perhaps you see it best if you look back at what we proved in case 1. So we want to estimate this left-hand side, L2 norm of W in F plus T gradient of W, L2 norm on F. This has to be estimated by the L2 norm of U on E. So let's start from the left side. So W in L2 of F squared plus, okay, and I put a lambda here to make things work, T gradient W, L2 norm F squared. Now this lambda in the end goes into the constants. Okay. First step, we somehow have to introduce the eta. We want to get this estimate. And this is where we need our estimate on eta that is valid on F. Where is it? Yeah, on F we know that our eta is bounded from below by this exponential function. So if you multiply eta with 2 times e to the minus this stuff, then you get something that is greater 1. So we can estimate this from above by the integral over F modulus of W squared, this is the L2 norm, times eta squared 1 over 4 e to the minus 2d over alpha t. We are on F here. On F, eta squared is less or equal. No, it's great. Eta squared is greater than this term, than the inverse of this term. So this is greater than 1. And this is just to let appear the eta squared to be able to use this estimate. Plus the same thing for the second term. This is lambda times the integral over F. Okay, t squared gradient W squared. This is just the L2 norm. And then just introducing the same factor, eta squared 1 over 4 e to the minus 2d over alpha t. Yeah, okay. Okay, so this factor is the same in both integrals, so take this in front. So this is e to the minus 2d over alpha t. Yeah, we also take a 2 here. Then we get so from the 1/4 I take 1/2 into the prefactor and 1/2 stays inside in order to get exactly this one. So there is 1/2 left, Rn modulus of W eta squared. So this is what remains here. W eta 1/4 is here and the exponential is here. Plus lambda times t squared 1/2 integral over f gradient W squared eta squared. So this 1/2 is in the prefactor, this in the prefactor, the rest is here. And now you see what is written here is exactly this one. So this can be estimated by the prefactor there. We have a 1/2 here. We have a 1/2 there, so this is e to the minus 2d over alpha t over 4 times the L2 norm on Rn of W. So this is what is here, squared. Okay, this already looks good. We do not need the L2 norm of W here. We need here the L2 norm of U on E to have our off-diagonal estimates. But this is again where our lemma 11.7 comes in, which tells us that so this is W. The norm of the resolvent applied to U, resolvent applied to U is W. And 11.7 tells us that W on L2 can be estimated by U on L2. So this is less or equal by 11.7. Then 1 over 4 e to the minus 2 over alpha td times U in L2 of Rn, but U is supported in E, so U in L2 of E. And what is now written here is simultaneously off-diagonal estimates for both our families of operators. You have the family W, so this is the family 1 plus t squared L to the minus 1 U, plus t gradient W, this is the second family, and both are bounded by some constant prefactor times e to some constant distance over t. I should write it like that. Distance of the sets over t times the L2 norm of U on E. And this is exactly off-diagonal estimates. So this is a technical proof, but the funny thing is the idea is genius because you have to find the right function, but it's easy. It's just testing the equation with the right function and then doing standard estimates, bootstrapping things, absorbing parts of the right-hand side to the left-hand side. But the main point is to find this particular test function that makes things work. Okay, so what we've achieved up to now is we've shown that these two families, the resolvent and t times gradients of the resolvent, both have L2 off-diagonal estimates for every elliptic divergence form operator. And yeah, now one might say, okay, so we have the same, in this context, the same behavior as for the Laplace operator. What is this? Why is this interesting? What is this worth? And the answer of this question will be on Wednesday. So on Wednesday we'll first show that there's a nice duality principle for off-diagonal estimates. Then we will meet even the third family of derived from the resolvents of L that has nice off-diagonal estimates. But then the main part of Wednesday's lecture will be to give you applications of off-diagonal estimates to show how these estimates are crucial and very, very useful to get information on our operators L that is otherwise very hard to prove. So this is what we will see on Wednesday. For today, thank you for listening and for your patience. Have a nice day.